So here are some actual examples that we're going to go through. So on this graph right here, on this titration curve, you're looking at two things. One in the red is 20 milliliters of a 0.1 molar HCl solution. And the blue is 20 milliliters of a 0.1 molar acetic acid solution. So both are same volume, same molarity, which means, of course, that means they'll have the same equivalence point, albeit at different pHs, right? So if we look at the HCl situation, right, it's 20 mils and 0.1 molar. And so you can see here at 20 milliliters of added 0.1 molar NaOH, we hit each of the respective equivalence points, okay? Because remember, 20 mils, 0.1 molar, and 20 mils and 0.1 molar will have the same H plus and OH minus concentrations. But now what I want to focus on is how we can actually do these calculations for the weak acid case. And we're going to do three different calculations. Number one, we're going to calculate a half equivalence point. Number two, we're going to calculate an equivalence point. And number three, we're going to calculate an excess titration point. So that's going to be three calculations. And it's going to be all based on this figure. And I've left plenty of room here to go through those calculations. Okay, so here we go. Example 16.5a, using the acetic acid NaOH titration curve on slide 16 that I just showed you. Calculate the pH of a 20 milliliter 0.1 molar solution of acetic acid when number one, number two, number three. So those are going to be our three calculation points. Okay, so let's get into it. Let's do the first one. I've got plenty of slide room here. And so what I want to do first is I recognize that I'm adding strong base to a weak acid. Acid reacts with base, okay? So this is going to be a before and after table calculation. So we'll say number one here. So I'm going to start with my reaction, CH3COOH, and I'm going to give myself plenty of room to work through all of this. And we know that that makes the acetate and water that I'll leave over here in the corner, and we know we don't really care much about water. Okay. So now if we look at the before situation, so let's say before, okay? So now remember, we've got to do the proper calculation of getting moles and comparing it to moles and then converting back to molarity. So we have our acetic acid is 20 milliliters of 0.1. Remember, that's 0.0200 liters, okay? And remember, this is 0.100 mole per liter. So I can start here by saying 0.0200 liters times 0.100 mole per liter. And we can see the liter and the liter will cancel, and that will give me the number of moles. Okay, so that's going to give me 0.00200 moles. I know that's a lot of zeros to carry through, but it's important that I get the right number of sig figs. Okay, so again, I got that just from saying 0.02 times 0.1 and 0.002, and I added on the extra sig figs because we need them there. So my hydroxide now, I'm adding 10 milliliters of a 0.1 molar solution. Remember that 10 milliliters is the same as 0.10 liters, okay? We'll make all of these 10.0, 20.0, and 30.0. So I'm going to say 0.0, 0.0, 0.0. Sorry about the sloppy mess there. I just want them to all have the same number of sig figs. So that's going to be 0.100 liters, which is our 10 milliliters, times our 0.100 mole per liter. And right, that's going to be 0.00100 mole. And hopefully you can see by now that's going to be the half equivalence point. And if you don't recognize that right away, the way that I recognized it is I've got this is called a millimole. mole. 2 times 10 to the minus 3 moles, 2 millimoles. So here I've got 2 millimoles, and here I've got 1 millimole. That's half. The hydroxide is half of the acetic acid. So that's how I automatically know that's a half equivalence point. Okay. And then we'll say these are all 0 and 0 initially. And so now I know after these react, okay, that it's the limiting reagent that's going to get reacted completely. So that means all of this is consumed, which means this same amount has to react. And then now if I look at the after situation, now I've got 0.00100 mole of this left. I've got 0 of this left, but we also remember that if I consumed 1 millimole of acetic acid, I have to create 1 millimole of acetate. So now I have 0.0100 moles of that. And if we recognize automatically that the pH equals the pKa right here, we could stop and just use that information, right? So here it's saying the pH at the midpoint is 4.75. So if we recognize we're at the half equivalence point, we could just say stop, we're at the half equivalence point, okay? But what if I didn't recognize I was at the half equivalence point and I wanted to go through this all the way? Well, now what I need to do is convert these moles back into molarity. So now I have to divide it by the new volume. And that new volume is going to be 30 milliliters. I got that because my original solution was 20 milliliters and I added 10 milliliters to it. So now I have to divide this by 30 milliliters, which is the same as 0.0300 liters. And this is 0.0300 liters. So now this becomes 0.033 molar, and this one is 0.033 molar. And now if I was solving this problem here, we can say pH equals, and the Ka for acetic acid is 1.8 times 10 to the minus 5. You'd have to be given that number, obviously. I'd give you that number. So pH equals the negative log of 1.8 times 10 to the negative 5. So I'm using Henderson-Hasselbalch, right? Plus log. And now that's just 0.033 divided by 0.033. That's going to drop out to 0 because the log of 1 is 0. And then now pH equals the negative log of 1.8 times 10 to the negative 5, which is the pKa, and that's 4.75 for number 1. And so again, that gives us that exact midpoint. And my numbers are the same as this titration curve. So here you can see that 10 milliliters, right, gave me that pH point. Okay. So the next one we're going to focus on is this equivalence point calculation. And I'm going to go ahead and we're going to transition that into a part B video.